Thanks. Good morning, everyone. Yeah, actually, I am going to, well, among others, but basically I'm going to kind of recap the first complexity course you ever took, but try to do so in a slightly different manner. So the title of this talk is Hardness for Problems, and what we are going to discuss is this somewhat new subfield of fine-grained complexity. Let me try to sketch the plan of what we are going to do in the seminar today. So in the first part of the talk, which will be roughly the first hour, I would want to give some survey of this subfield. So this would kind of be the definitions, going over what we care about and why, giving some overview of the landscape, what we know to do. And we will also get some very basic techniques. So we'll go over like the first things that people show in this type of field. In the second part of the talk, though, which will be roughly the second hour, we're going to talk about the new results. We're going to discuss some new tools that, in a very summarized way, help us take some hardness or fine-grained hardness result we would show for exact problems and translate them to approximation problems. Mostly, at least. Okay, so as I said, the next hour is going to feel like we are back to complexity 101. So what do we know about problems and hardness of problems? So fix your computational model of choice, whatever you prefer. Usually using arguments of diagonalization, you can show that for any nice enough model and function T, there are some problems that you can solve in time T of n, but not solve in time T of n, let's say, to the 1 minus epsilon for any epsilon which is larger than 0. So this is true for almost any computational model you can think of. The problem is that we usually really don't know how to find these problems, or don't know how to say similar things for specific problems. So similar statements for specific problems are hard. We should take care of the use of the word hard. But let's give some example that will be useful for us in a few later occasions. So maybe the most classical of problem that we think of as hard is the satisfiability problem. What is that? You get a Boolean formula on n Boolean variables, and you want to know whether or not it is satisfiable. So, okay, just write n variables and assume that the problem definition is fine. What do we know about this problem? So basically, we don't know almost any improvement to the most naive approach you can think of. So the most naive approach you can think of is, let's ignore things that are sub-exponential for now. Most naive approach you can think of would just be to enumerate over possible assignments and there are improvements to that, and they are clever, but the improvements we have are sub-exponential. This means we can divide this by something that is not better than anything less than 2 to the n, not any constant less than 2 to the n. We can also think, and this would be useful very soon, of KSAT. This is a restricted version of this, where the formula is given in a KCNF form. Reminder, KCNF form means that we have clauses with n between them. In each clause, we have some literals, let's say x1, some xk. Literals can be variables of their negations. KCNF form means that we are in this type of a CNF form and that each clause is of size at most. Okay, so actually for KSAT we can do a tiny bit better. What do I mean by a tiny bit better? For every constant k, we can solve KSAT in 2 minus epsilon k to the n. And this thing depends only on k, so as long as k is a constant, this thing is a positive constant. Let's put some citations. So I think that the first such result is for it's by Munien and Schweckenmeyer. This is 85, and they showed something like epsilon k is larger than 1 over 2 to the k. A big breakthrough is the algorithm of Puri, good luck, Zaps, and Zane. I think this is 99. They basically showed that it is actually something like 1 over k. And then with our algorithm, this is understand. And I think that there is very recently another improvement for k equals 3, but this dependence remained. And the important thing to take from this thing is that even though we can improve exponentially the running time of KSAT when k is fixed, in all of these algorithms, as k goes to infinity, this again converges to the same 2 to the n. So even for KSAT, if we think of the clauses as being large enough, we don't have anything better than the naive solution. So we might ask ourselves, okay, so we have this very basic problem that everybody cares about. We think that it is hard because we can't solve it in any way that is better than the naive ones. Then what about lower bound? And the answer for that is very sad. The truth is that we know nothing. We don't even have a proof that you can't solve this in linear time, for example. So this is how bad the state of things is. So what do we do about this? So when I say what do we do about this, I mean what did we do about this? And the solution we had for that was to think of conditional lower bounds in a sense. Right, so start thinking on conditional lower bounds. What do I mean by that? I mean that we figured out that there are some interesting complexity classes such that we can reduce problems within them to each other or to some of these problems. This means that we managed to say things of the form, we believe that something terrible cannot happen. We believe something like P is not equal NP. And we can say a lot of things like, if problem X would be solved fast, Right, so this is a very typical type of statement, surely in the early days of algorithms and complexity, but also now. And the way we interpret this type of statement is problem X is R. This is how we view this. We view this thing as a type of a lower bound. It is conditioned on something, but we believe this something, so we are fine with this. And well, I don't know if we really need a lot of citations, but maybe just for being complete. Let's cite Cook-Levin. Let's cite Karpf, showing that there are many problems that are NP-complete in that sense. Okay, and this thing is actually groundbreaking in a sense. It is arguably the biggest export of theoretical computer science to every other field. This is something you view in a lot of places. Why? Because this statement translates to many occasions. As we said, we think of this meaning problem X is hard, but this a lot of times meant that people view this as problem X is hard. Then let's restrict the problems. Let's look at heuristics and things like that. But the problem is that this type of statement comes up only also when the definition of hard is very far from being NP-hard. Right, so the same type of notion, the same type of, at least the way people treat this, this statement would be the same even if this hard would not be interpreted as being NP-hard, but in some occasions even being worse than linear. Right? Hard means we can't do it. So I have maybe some examples, probably a lot of examples, but some example that I found interesting is that if you don't know this problem, it doesn't matter, there is some string problem called local alignment. Right? This is something that is very important in computational biology. This is used for comparing DNA sequences. And it has a very, very simple dynamic program that runs in time and squared, but this is very far from being enough in practice. If you have these two huge DNA sequences and you want to compare them, you can't do anything quadratic. So people worked a lot on heuristics for that. And you can actually see that if you count citations for the dynamic problem paper and citations for the best known heuristic paper, then you see a factor of, so the heuristic paper has this number of citations, the dynamic program, not many people care about. So the way we think of hardness might need to be different than just NP-hardness. This is actually relates to a conversation we had at lunch yesterday. Right? We talked about if aliens would have developed complexity theory, would they develop the same notions? So maybe the notion of hardness would be different. It's not clear that NP-hardness is the most natural hardness to think of. So what our objective is going to be is to find some notion of hardness that is much more fine-grained in a sense, much closer to being something that is very quick versus something that is not very quick, and not just polynomial versus non-polynomial. Okay, so what our goal is, let's try to formalize it for a bit. We want to take some problem. Maybe it runs in, let's say we have an algorithm that runs in square time. So you can generalize this to anything, but let's begin with that and say that it can't be solved in time that is polynomially less than that, let's say n to the 2 minus epsilon or any epsilon larger than 0, unless. And so we would want to have some type of conjecture or something we believe in similar to P does not equal NP that would be enough to generate statements of this form. This is what we are going to call FineGrain. And when I said we are going to kind of repeat over the first complexity course, my meaning was that now we kind of need to both find these conjectures to start from, conjectures that would allow us to get this type of statements, but also we need to revisit our definition of reductions, for example. Right? Because when we talked about NP-hardness, reductions were polynomial reductions. Obviously, running something polynomial is not going to be enough to get something like this. So we are going to look at these notions of fine-grained reductions and some conjectures that imply these things. Okay, and then in general, what we would hope to get is one problem or very few problems that we have a lot of reasons to believe that are hard that would imply the polynomial hardness of a lot of other problems for which we are stuck for a lot of time. Right? We are kind of wanting to unify the reason for the hardness of problems we care about. Any questions up to this point? Just like what we're trying to do. Okay.
So why are you aiming at n to the 2 minus epsilon and not something stronger?
That's actually a very good question. The reason that we are aiming for this type of things and not for things that are stronger is that in many occasions you do have this type of very slight improvement. So as we said, for a SETH, for example, you can get something like 2 to the n over something that is sub-exponential. I'm not sure about local alignment, but things like edit distance and other string matching problems you can get n squared over some polylog, things like that. So sometimes there are clever tricks that improve over that. So we are trying to get something that would bypass these small improvements. That's a good.
And another question, so what is your computation model?
Another very good question. You do need to pick one. Usually we would work with word RAM or like the RAM model. This makes sense, but you can also work with Turing machines or anything else. Most of the reductions would survive either. I mean, we will notice if we do anything weird. We are trying not to. Okay, so what conjectures should we start from? Let's remove this. So ideally, we would want to get all of these things from the same old things we believe in, right? The ideal thing to say would be that this unless means unless P does not equal N. We would be very, very happy with that. The problem is that this is difficult to use. It is not completely not plausible, but it sounds difficult to do something like this because just the definition of polynomial versus not polynomial does not distinct naturally between, obviously not between n squared and n to the 1.9. So some starting point that became very popular in recent years are some strengthenings of P does not equal NP. Right, so we want to strengthen P does not equal NP, and what do I mean by that? By that I mean we want to make it more quantitative in a sense. So maybe the most popular conjecture here is something called SETH. Let me find the citation. This is introduced by Affiliation. Factorial. And same in 01, I believe in 99. And what is this conjecture? This conjecture is basically that what we saw happening over here is what should happen. So this conjecture is for every epsilon larger than 0, exists some k such that k SAT not be solved in 2 minus epsilon. Yeah. This is basically saying that these epsilon k's are going to 0. SETH means the strong exponential time hypothesis. Without the strong, this is just saying that it takes some exponential time, without saying that it should be actually 2 to the n, which can also be used for many things, but for the fine-grained things, this is much more helpful. Something to note about this conjecture and other conjectures we are going to use. It is not necessarily believable. Many people do not believe that this should be the case. I want to argue that this doesn't matter. Why does this not matter? Because even if we wouldn't bet our lives on this or other conjectures being true, everything that I would write as a conjecture is something that breaking would be an amazing breakthrough in some field. So this means that if this is not true, even if the world doesn't collapse, at least you will get like a lot of prizes.
So what would be the consequences of this being false?
So it's actually not completely clear. There are consequences of SAT in general being solved in this time, but K-SAT is not exactly the same. Like you could imagine that there is some FPT type of running time. I'm not sure if this has any consequences. I mean, if you would have something like 2 to the K times 1.99 to the algorithm, I'm not sure if this implies the same. So if you would have this for general SAT, it does imply some circuit lower bounds and things like this. I'm not sure about the K-SAT version. Yes. Another thing is that a lot of the reductions we are going to see are actually going to go through several problems, and some of them are likely to be harder than the conjectures we start from. But this would be a very popular starting point, and let's maybe have some flavor of what we get out of this. So, for example, we talked about this type of statement. So this type of statement is true, assuming SETH. For several problems, for example, this local alignment problem. Happens to be that indeed this dynamic problem is the best thing you can do, unless you can break that. Other things like edit distance, for example, this is another string matching problem. This again goes to Yuval's question. For edit distance, you can get some shaved polylog. So this shows that, yes.
So this is a bit of a question about strengthening P versus NP. If you had asked me a priori, like what is the exponential version of P versus NP, I would say something like circuit SAT is not in time, like 2 minus epsilon to the n. I guess this assumption just isn't as useful as the K-SAT version.
It can be used for some of the things. Something about K being a constant ends up being very helpful in many of the reductions. We will actually see a reason for it soon enough. Just the structure is nicer. But if you work hard enough, you can get things for more difficult assumptions. Okay, and we will have also some other conjectures. So let me just state 2 others, but I will not dive too deep into any of them, just not to make you all bored at this point. But arguably the 3 most popular conjectures for this type of reductions are this SETH thing, Another one is the free sum conjecture. This is that if I give you n numbers, let's say of polynomial size between -n to the 4 to n to the 4, you can't find a triplet that such that two sum to a different one, or that all of them sum to 0. These things are equivalent. So the conjecture is that this is not in time n to the 2 minus epsilon for any epsilon larger than 0. It is in time quadratic quite easily. For example, go over pairs and then do a binary search for the last one or something like this. There are some, again, polylog improvements over the quadratic times. This was a major breakthrough, but still people do not believe that it should be improved further than this. Another popular conjecture is about all pairs shortest path. This means that I give you a graph and I want you to compare between two vertices the shortest path going between them, or at least the length of the shortest path going between them. The classical algorithms take time and cubed, and again, polylogarithmic improvements do exist. A very long list, very impressive things were done to improve this polylogs by a little bit, but we don't know anything that is really better than n cubed, and we don't believe that there should be. So this is kind of the three main conjectures that we are thinking about. And if I forget talking about this, please ask me in the end, why do we need more than one conjecture? Because there is some unfortunate explanations for that. Okay, so I did prepare in advance a book full of citations. Let's try to very quickly go over that. This is a tiny bit of the papers working on this type of fine-grained complexity lower bounds. Since then, there have been hundreds of papers on this. These are kind of the earliest ones that either developed tools that are used in this modern type of subfield, or papers that were the first such lower bound in some field or some regime, but obviously there are many others afterwards. I have here some like list of SETH lower bounds. You can see things like K-dominating set, the diameter of a graph, checking whether a tree is isomorphic to a subtree of a different tree, this local alignment, edit distance, closest Hamming pair, geometric problems like the Fréchet distance of things. Maybe the notable people to note in all of these are Ryan Williams, Virginia Vasilevska-Williams, and Amir Aboud. You can see that they appear here frequently enough that I also abbreviated their names after some time. So yeah, that saved a lot of chalk.
On the SETH part to go through orthogonal vectors, or are there
No, so not all of them, some of them. We will soon talk about orthogonal vectors, but there is some in the same way that this happens with NP reductions. There are some central problems that we reduce SETH to, and we use them to reduce them to other problems.
Can you remind us again?
Yes. So the three-sum problem.
I know maybe other people don't, not what they are, but I'm happy to hear that too. But the relative strength of the assumptions
in comparison to each other.
Yeah.
Okay, so we will talk about this a bit in the end, but the bottom line is that we have no reductions between any of this, and that there is, at least for some of them, there are good reasons why. So we have.
think they're incomparable. People actually think they're incomparable.
So if you believe something that is slightly stronger than SETH, you can show that SETH can't reduce to any of the other two, for example. Okay. Yeah. Yes.
Is there some principled way to come up with these like three hardness hypotheses, or is it just like empirical, we know that like.
So I can, like, historically, the three-sum conjecture, for example, was actually used much before this subfield emerged. It was used in the 90s for a lot of computational geometry, lower bounds, things like, I mean, things that in a sense appear very natural, things like collinearity checking, if you have 3 points that are on the same line. So in the 90s, it was used for this type of geometric problems. Big breakthroughs here were using the same also for combinatoric problems where you don't actually sum numbers up, because this was kind of the, I don't know, the more obvious thing to do. It's interesting that, for example, three-sum now can be used to show that listing many triangles in an unweighted graph is hard and things like that. APSP is actually equivalent to a lot of problems like Boolean matrix multiplication, finding a negative triangle in a graph. So all of these are somewhat useful. It is worth mentioning that for more than a few problems, we can actually have reductions from more than one of these conjectures. There are also problems that are harder than all 3 conjectures, harder from a couple of the conjectures. And that's not surprising by itself, right? You can just concatenate the problems, but there are not really, but somewhat natural problems that are harder than several of them, and they are used for other reductions. Okay. Any questions so far? If not, our next goal would be to try to give some examples of such reductions. Maybe like the most, like the earliest or the most basic examples for such things. Yes, and as Roy mentioned, for example, we're going to see, to begin with, some central problem that we can get hardness for from SETH, and then use this problem for other reductions. So we really do follow what happened with NP-hardness in a very close manner. Okay, so what is this orthogonal vectors problem? So orthogonal vectors are over here. I think that in terms of this reduction, the citation is probably again Ryan Williams. I think this actually appears in his paper from 2005 already. It's phrased a bit differently, but yes. So what is this problem? We are given, let's say, 2 sets. AB sets of size n of vectors that are binary and d-dimensional. So we have 2 sets of vectors. Let's think of D as something that is larger than log n, right? Because we don't want to necessarily have multiplicities, but not much larger than log n. For now, let's think of it as a polylog. For example, the problem is to find out whether there exists some A and B and B such that A and B are orthogonal. And actually, I take this over the natural numbers. So I mean, by orthogonality here, I mean that you can think of it as they represent disjoint sets, in a sense, they have different support. It's also interesting when you're doing it over other fields, but this is the simplest and most useful definition of this conjecture. Okay, so two sets of slightly short vectors, and we want to say whether or not there is an orthogonal pair. What is the naive thing to do? Like, what is the first algorithm to think of? Just check, right? And it was, I don't know how to call it, like, okay, just say that the naive thing is n squared. I ignore d because I think of d as a polylog and I ignore polylogs. Okay, so the first thing we would like to show is that if SETH is true, then this is tight. Tight in the same sense of the things we said before. Right, so theorem if SETH, then no n to the 2 minus epsilon O. Okay, so how would we prove this? This is a simple reduction. So we are going to do the following thing. We start with a K-set formula. All right, we start with a K-set formula for K, which is larger than what we shouldn't be able to solve in this time. All right, so start with K-set formula, let's call it Phi. It has, maybe I'm overusing the letter n, but never mind. It has n variables. We're going to partition the variables into two sets. Let's call it like XA. This is a completely arbitrary partition of the variables, two sets of roughly the same size. And now what we are going to do is to define a vector in the first set A for every possible assignment to the variables in XA, and we'll do the same for the set B. Right, so what the set A is going to be? A is going to be some vector for every possible partial assignment to XA. So for every phi prime from XA to 0, 1, for every alpha, which is an assignment from the first set of variables to 0, 1, we are going to define some vector that is corresponding to this assignment. And what is VA going to be? So the length of VA is going to be the number of clauses in our formula. Like that. The length is going to be M, and M is the number of clauses in the case of the formula. And the way we define VA is that in the ith entry, this corresponds to the ith clause. We are going to have 1 if this partial assignment does not satisfy the clause. And 0 otherwise. Right, what do I mean by that? A clause is just the end of some literals. When it is satisfied by a variable, by at least one variable. So if some variable that was assigned a value in alpha with this assignment satisfies this clause, it will have 0, otherwise it would have 1. And it is quite easy to see that you would have a pair of orthogonal vectors if and only if you can satisfy everything.
By length, you mean the D?
Yes. So, yeah, and the length of the vectors, like the dimension of the vectors, is the number of clauses. All right, are we fine with this translating satisfiability to orthogonality. Okay, good. What is the size of everything in here? So the size of A and B is 2 to the n over 2, right? The size of D is the number of clauses. What is the maximal possible number of clauses? This is at most something like n to the k, right? This is where it is useful that we are looking at KSAT, and this thing is polylogarithmic in depth. Right, so we can think of this thing as a big N, and if we could solve orthogonal vectors in big N to the 2 minus epsilon, then we could refute SETH. Okay. Maybe a thing that is worth noting, it is not completely crucial at this point, but it is a very useful tool for other things. So I will mention it anyway at this point, which is the specification lemma. This is again with Pagliazzo and Zane, same paper. This is another reason to look at KSAT. They show the following thing. They show that if you have, I'll write it maybe not in a very formal manner. If you have a KSAT formula phi, and any epsilon larger than 0, then you can translate your formula phi into 2 to the epsilon n formulas, like the conjunction of 2 to the epsilon n formulas that are also KSAT formulas. Let's call them like theta 1 to theta s, such that for every I, the size of these formulas is bounded by some constant that depends on k and epsilon times the number of variables. This means that if I have a KSAT formula and I'm willing to pay 2 to the epsilon n for some small epsilon of my choice that is a constant, then I can actually assume that the number of clauses is linear in the number of variables. This means, for example, that this doesn't have to be a polylog, but it is actually logarithmic. Right, so the orthogonal vector conjectures, we can also just assume it for log n to the 1.5, for example, and this would be already enough for, I mean, this is already harder than any than SETH for any k. It was useful for later reductions. This reduction, as you see, it is not completely crucial, but I think that the first example in which it was crucial for the reduction is our sub-tree isomorphism paper. Later, it was crucial in several other things, that this is linear and not anything more than that. So going back to Raoul's question, this is another reason that looking at KSAT is somewhat more structured and easier to use. Okay, let's see. Yes.
Would you go for anything better than this, or
Anything better than what?
like the parameters, like the C of K epsilon? Like, is that important, or does it?
So I mean, I didn't even write what C of K and epsilon is. For this type of consequences, we don't care as long as it's a constant. I mean, in OV in general, you can't really hope for anything that is really less than logarithmic, obviously, because then you just don't just have repetitions.
also mention you could consider other fields over which you take the because it's still SETH required.
So depends on prime fields with only two sets. It is not hard if the field is something like. So if it is not a field but a ring that is I don't know, like Z6, it is not. It is hard for fields. It is not hard if you have more than two sets. Then it is hard again. So it gets a slightly bit more messy when you add these things, but this ends up being useful for many reductions, as we are now going to see. So now we're going to see some example from a reduction from orthogonal vectors to a graph problem. Again, this would be like one of the easiest and first ones. So the problem we are going to discuss is a graph diameter. What is the diameter of a graph? The diameter of a graph is the maximum over all pairs of vertices. Let's call them U and V. Of the distance, like the shortest distance in the graph, between U and V. This is the standard definition of diameter in everything. So this is also the diameter of a graph. How fast can we solve diameter? So the upper bounds we have are either you can solve this in the number of edges times the number of vertices. This is just by doing a shortest paths algorithm from every vertex. Then you have all of the distances and you can find the best one. Another solution uses fast matrix multiplication. So this runs in times n to the omega, where omega is the fast matrix multiplication constant. Both of these things, even for sparse graphs, take quadratic time, even if matrix multiplication is linear, and so on. So what I would say is that this is at least n squared for sparse graphs. And our goal would be to show that this is tight. That even for sparse graphs, you can get n to the 2 minus epsilon for computing the diameter. So theorem, no n to the 2 minus epsilon diameter, even graph is sparse. And as I said, we are just going to reduce. Yes.
Less what?
Strong. So SETH, but actually orthogonal vectors. As we noted earlier, because of all of these reductions go through different problems, and it is true that for the SETH reductions, for example, many of them you go through these orthogonal vectors or other central problems. It could also be that something like the following is true. It could be that SETH is not true, but orthogonal vectors is still true. And then maybe out of these reductions would still survive, even if one of these things doesn't hold. Okay, so we are going to reduce an instance of orthogonal vectors to an instance of graph diameter. And how would we do that? So we have our sets A, B, of size n of d-dimensional vectors. We are going to create the following graph. So our graph is going to have 3 parts. This part is going to correspond to A. This part is going to correspond to B. This part is going to correspond to, obviously I want the dimensions, I don't know how to call it. This corresponds to D in a sense. Okay, so what do I have in each of these parts? So here I just have one vertex for every vector in A. So let's think of them as A1 to AN. Here I have one vector for one vertex for any vector in B, as B1 to Bn. And here I just have vertices for the dimensions. So I have vertices U1 to UD for each dimension. How do I construct this graph? So each AI is going to be connected to each UI such that this coordinate is 1 in the vector. All right, so AI connected to UI, UJ, if and only if AI and the J coordinate is 1.
All AIs and BIs are 0, 1 vectors now, right?
Yes, yes. I mean, the way we proved the SETH hardness for orthogonal vectors was binary vectors. We stay with binary vectors. And we do the same for B. So these things are also connected like this. And we need one last thing. We add 2 extra nodes, A and B, like little a and little b, which are connected to everything in A and everything in B respectively, and also connected to each other. Why is that? All right, so let's see what is the distance between AI and BJ. So if they are not orthogonal, if they share a neighbor, then there is a path of length 2 between them, right? Just go to this shared neighbor to the other one. So 2, if they are not orthogonal, and if they are orthogonal, then the shortest path is going to be of length 3. And because they have no shared neighbor, so they would need to go through this gadget where above. And you can check that for any pair that is not one from A and one from B, the distance is going to be the distance is going to be 2 as well. Right, like these two are connected. This is connected to anything in here, and there's a length 2 path to everything in here. These are connected to everything here, and yes. Okay. Is it fine? Yeah. So with these type of things, is this okay? Do we need to go over anything? If this is true, it means that the graph diameter is going to be either 3 if there are a pair of orthogonal vectors, or 2 if there is no pair of orthogonal vectors. And that's enough. And this shows that computing the diameter again is as hard as orthogonal vectors. The number of vertices is like 2n plus something small. The number of edges is 2n times d, which is again something small. So everything is so this is actually not orphan. This is O tilde. Okay, you can make this also exactly orphan if you like subdivide edges and make things a bit larger than this. And something to notice about this reduction is that it actually also shows that, because this is what we have in here, it also shows, quite that small. It actually also showed a 3/2 minus epsilon hardness of approximation. Right, because if you could approximate better than this, you could distinguish between 2 and 3, and this actually happens to be tight. So there is a 3/2 approximation that runs faster than quadratic time, but also this is something to keep in mind, because in the next part of the talk, when we are going to talk about hardness of approximation, we are kind of going to face a similar problem to what this very simply shows, which is that a lot of times the approximation factor you get comes from the difference between the yes case and the no case. And if you have short cycles in places, then this would make this difference small. So basically what we are going to try to do next hour is to show techniques for kind of eliminating short cycles that you don't care about. Okay, any questions about anything? If not, then let's say 2 last sentences and then take a 5-minute break. So these 2 sentences are about like why these conjectures, why not less, why not more, and so on. So there are very good questions to ask here, very good open problems. For example, we would indeed want to have more grave consequences for what happens if the conjectures we're using are not true. It would be better to have some conjectures such that we also know that if SETH is not true, then the world collapses. We still don't really have that. Something, as I said, we do have is that we do have some problems that can be reduced to from several of these things, and people believe them more. We have problems that people believe more or less, but it would be nice to have something that is very, very strong in complexity consequences sense. So this is an interesting open problem. The second thing I wanted to mention, and I will not dive deep into that, is that there is a reason we need more than one conjecture. And actually, I don't even want to write it down to not be required to write things too formally. But for SAT, we don't even know, and this relates to some talks we had here very recently, we don't even know how to refute SAT non-deterministically in time that is much better than 2 to the n. So if you have a SAT formula that is unsatisfied and you can use non-determinism, you still don't know how to prove that it's unsatisfiable in less than 2 to the n time. There are some consequences of what would happen if you could. And if you could do so deterministically, it implies some circuit lower bounds. So some people believe that, some people don't believe that. People have good reasons for both. But if you do believe that, then it means that SETH can't be reduced to the other problems. And the reason for that is that the other problems do have much quicker non-deterministic algorithms.
So could you say again? Are you going to write that down or are you just going to?
Yes, okay. So SETH is a stronger conjecture, which is need 2 to the n in the same sense as before, no 2 minus epsilon to the n, to non-deterministically refute SAT.
That's like
Another conjecture.
ASAP or
Let's say even case at for large K, but yes. If you believe that, then you can't believe that SETH can be reduced to the other problems because the other problems do have much quicker non-deterministic algorithms. For example, because okay, I don't want to get into why. Maybe some problem to keep in mind if you know like problems in graph algorithms is max flow. We don't have a linear algorithm for max flow, but proving that the flow is less than something is easy because you have the max flow mean cut theorem, so you can get some evidence for the flow being at most something. Proving that the flow is at least something is also easy. Just give a flow and check that it's at least this thing. So in a similar fashion, these problems also have fast non-deterministic algorithms. You can prove the solution much faster than the conjectures, and this means that they can't be reduced from SETH if you don't believe that SETH should have this type of thing.
Problems that have fast non-deterministic algorithms are the small ones or the big ones, like 3-sum and APSP, or?
Yes.
Okay, 3-sum and APSP.
Yes, both of them have. Yes, like faster than that, faster than the conjecture. Yes.
Could you hope to reduce 3-sum and APSP to each other, or?
There is no known reduction. I don't think that there is a similar reasoning, but there is no known reduction. Yes.
That's what I'm sure I understand you. It's not like they can be solved non-deterministically, three sum and APSP. It's that they can be refuted or.
I mean, being solved non-deterministically kind of means that given some evidence, you can check it in a faster time.
So, but I mean, it's clear that for three sum I can get the triplet and check.
Yeah, but yeah, also in the other direction, yes.
Okay.
Yeah, I mean, for APSP, it's less clear in both, yeah, right? But for free sum, yes, you can refute it also. Let's do that. Okay, let's take a 5 minutes break and reconvene for new stuff.
You definitely need that case that, not just for that, right?
Yes, yes, and also like let me, I mean, if it is written on the board, then I also will write the citation.
It's basically what you wrote for SETH, you just
Yeah.
tap on non-determinism.
Yeah. Good assumption.
Yeah, also, I mean, it's not true for, like, if you look at Arthur Merlin or Merlin Arthur, this is not true. Like this thing, so.
How fast is the reset?
So it's it was done after the decision complexity of n to the 1.5 of free sum, so it can be done definitely in that time. This was later improved by Lovett and people, like the decision tree complexity of free sum. Some big breakthroughs in free sum came from there is a short depth decision tree for free sum.
When the depth was, you said 1.5 to them, is that what you said?
N to the 1.5 for free sum,
Okay. So
less than quadratic. I mean, this doesn't translate to a faster algorithm because you don't know how to compute like the tree, but using this, you can somehow get the non-deterministic algorithm.
Yeah, but the decision tree was improved to quasi-linear though.
Yes, so what I want to say is that the decision tree was improved. I think that this was after this result I'm now citing, so I don't know if the same works with the improvement, but it is like at most n to the 1.5 anyway.
When I convert to the n steps, what does it give me? Instead of 2 to the n?
What do you mean?
Sorry, I don't know how to do the conversion.
So there is no fast refutation for SETH. What I'm saying is that there is a fast refutation for free sum, faster than n squared. And we don't believe, or some people don't believe, that there shouldn't be a fast refutation for SETH. So it means that you shouldn't be able to reduce SETH to free sum because then you would have a fast refutation for SETH as well.
The point being, I guess you can't reduce n SETH to three sum, for example. You couldn't really do it in a direct way because.
Yes, okay. There is also a question of what exactly are the reductions. Like the reductions need to be, yes, you need some, if you define reductions in a nice enough manner, then this is true in general for this reduction. A long list of names.
So what
Yes.
if we could, what would it give you instead of 2 to the n for n sub? So that's what I'm trying.
Oh, so it would be at most 2 to the 3/4 n, but maybe now it is actually n over 2.
That's for what, k being what?
For k as large as
No, it's not that long.
for every k. For every k, it is a large constant. I mean, again, it could be different. It could be different.
Yeah, I think so.
So I wanted to check that there's no conflict because I'm speaking a week later at the correct.
Oh, really? Is it, I mean, that's.
Yeah, that helps.
That's
Oh, thanks. Yeah, I mean, sorry for it's just busy writing the names.
Are you gonna be in person for either? Or
Yes, I just didn't want to, especially being on video, I didn't want to cite something for writing.
Quasi-linear is not this one. It's
No, so the quasi-linear is not related to this, it's about free sum. So free sum has a,
for three sum. It said there was 2 results for 3 sum.
yeah, so free sum there was like a huge breakthrough, no,
Yeah.
this is
I might be able to.
after the huge breakthrough for free sum.
A little bit better than n squared.
Simpler.
Yes, but it came with a decision tree complexity of n to the 1.5, that was the original one. Then there was a sequence of improvement getting all the way up to quasi-linear by log other people. The latest improvement is after this page. They don't use it. But maybe they could use the best one and get the. I didn't check.
It's weird to me.
Yes, what do you?
Quasi-linear is, which is so good, only gives.
No, so like I didn't use the quasi-linear linear. Like if you would use the quasi-linear would give you half.
But that's, yeah,
Fine, because this would be like n instead of n squared.
I got you.
The 3/4 was assuming.
I should think of n as n squared.
Exactly.
This is not in person. Something that goes from. Yeah, that's right. I was in New Jersey. Efficient that
And people think
typically.
like you can't get decisions from below n.
I mean, it's you need to. How would you decide about reading?
No idea.
To see the same behavior.
I think you can prove.
And it shows why we're having trouble with it.
And then the other way around, is there any evidence for the other way around?
Not that I know of.
So it could be,
Yeah, I
could
guess.
be that n says
It's actually
stronger
good.
assumption than 3 sum.
I think that's.
Yeah, I mean, could be. Also, it could be, there is some other problem that implies everything is implied by everything.
Did this on lunch? Maybe I'll hang out for an hour.
The discussion get resolved.
Yeah, I just. Yes, so
Yeah.
and it's.
When I tell you why. You did
Yeah,
it,
Yeah.
That's really.
All of these things. Yeah, usually I guess they.
Austin.
Unfortunately.
It's the usual.
Because none of the.
As fast.
They're keeping them away from the.
Yes, yeah, there's a magic link.
Yeah, I was.
You're taking actually.
Actually, or maybe we can cut to, actually need a minute.
I don't need them yet, but.
So like you
Essentially.
everything under regular. EQ?
Yeah, although. Yeah, I was really paying.
No, you cannot, it cannot.
There are not as clear as this.
I mean,
There are things for.
it cannot be just.
So the type of things that use regular ETH are things that saying that have some FPT problem.
Way down.
Say that the dependence on n is the same. Sometimes I can because I would have like some function I don't really care about of k, then something fixed depends. So this you might like some things like this you are able to do
So is
it.
it if you have an ET?
I guess not this bad, because the third term will be the mechanism, the second term will be the same.
It's definitely weaker than SETH.
No, no. Is it know that it's
The
weaker?
I was not gonna no,
Going well.
not
How are you?
not exactly.
Still.
It's not exactly the same.
Good. Oh, yeah. That's very weak.
They do better than some.
They become tricky.
I think we should start
I think the
getting
maximization problem is.
Everybody ready?
I can.
All right.
Okay.
It's not a problem because.
Okay, thanks for not running away in the break. Now we are going to present slightly more newer or slightly more complicated stuff. So if you do want to stop me for anything about the rest part, actually let's do it later anyway. And what I'm going to present, okay, this is based on works with Zamir and what I will try to sketch is some new techniques that, as I said, resolves some of what was like major problems in this fine-grained complexity field by doing something of the following form. I'm going to phrase something that is very, very informal. You will soon realize the reason for that. The exact statement is quite technical, but in essence, what I'm writing is what we are doing, and we will first try to understand why is this helpful and how do we use this to solve things. We'll also say what things. I'm very ambiguous at that point. So we are going to show the following thing. I'm going to say that a graph G can be efficiently. Maybe I will add like red note on everything that hides things that I still don't want to say. So any graph G can be efficiently transformed to another graph G prime. This is actually also somewhat fishy because sometimes it's not going to be exactly one graph, but a collection of graphs, such that the following holds. The first thing we would want is that the existence of triangles is preserved. Right, so exists a triangle in G, if and only if exists a triangle in G prime. No notes about this. This is actually going to be true. But the other thing, and this is going to be the important thing, is that G prime doesn't have, and this gets even 2 notes because it's not always completely not, it's sometimes going to be a small number, but G prime doesn't have any CKs. This is a cycle of length K for K, which is 4, 5, all the way up to a constant of your choice. So this constant will obviously, the efficiency and the number and things like that will depend, but let's just go over that in essence. So the essence is going to be that we can take a graph and efficiently get rid of all small cycles without, at least unintentionally, removing any triangle. Maybe looking at the less simple reduction we've seen can give us.
You preserve the count of the triangles as well?
What?
You preserve the count?
No.
No. Okay.
Just the. Actually,
you would remove some triangles as long as you know.
We actually preserve a bit more. We will know for each edge if it was a part of a triangle or not.
And efficient, did you say what efficient means?
No.
No. Oh, this is
No. But okay, what's 1 second? What's going to be the point of that? So one thing to have in mind before we are starting to sketch how is this going to be useful is the last reduction we've seen, in which we need to separate something like between 2 and 3. Having such type of mechanism would allow us to make this gap between the yes case and the no case basically as large as we want. So this is kind of going to translate this exact fine-grained lower bounds to lower bounds for any constant factor approximation. Yes, Roy.
The application that you just mentioned is intuitively clear. This looks like a very natural statement or question, so I was wondering if it has broader motivations or application.
Yes, we are going to list several applications and motivation. Okay, so let's put this out. At some point, I will write the exact statement, then you're going to miss this statement. But first, let's give motivation. Let's see what we get out of this. So we're going to list a few things we can get out of this. The first thing, which is a big open problem, not only in this fine-grained regime, is something called distance oracles. So what is a distance oracle? A distance oracle is basically the following question. I give you some graph, usually sparse, you can assume it is sparse. I want you to pre-process the graph in some time. Usually I also care about how much space you are using to remember whatever you have after the pre-processing in your memory. And then using this pre-processing and whatever you saved in your memory, I want you to be able to answer queries about the distances between two vertices. And usually this would require some approximation. I mean, obviously if the graph wasn't sparse, but even if the graph is sparse and you want to maintain the information very efficiently. So the big question here is, what is the right trade-off between what approximation you can give me to the pre-processing time, to the memory, to the query time. Okay, and I'm not going to cite everything because there are literally dozens of papers about these distance oracles. I will cite maybe I don't know if the latest, right? The most major result on that, which is the paper of Rashko, Oditi, and Goruk from 2012. And they basically show the following thing. They can get K approximation in pre-processing and memory. That is m to the 1 plus some constant times 1 over k, and the query type is constant. Okay, so this kind of gives you a trade-off of how much memory in pre-processing time you need to preserve a k approximation. M is the number of edges. Yes, all throughout. Usually I use m for number of edges and n for number of vertices. K is a constant. Let's think of k as a constant. Otherwise, the terms are a bit more complicated. And also in their paper, they show some conditional lower bound. So I don't want to get into the exact problem they reduce this from, but they show a conditional lower bound from something called SETH disjointness, some popular conjecture, or actually it became popular afterwards. I'm not sure if it was very, very popular for that, but they show some conditional lower bound showing that what they show is tight, but only up to k equals 3. This is actually a bit less ridiculous than it sounds. Like their k doesn't need to be a constant, so they actually show that like their the curve that they get for this trade-off is tight as long as the stretch, as long as the approximation is up to 3.
Can you just say what the SETH disjointness?
I actually don't want to. I don't want to, but it is, you know, so this one is, I think it is some assumption about you have sets in your memory. You want to know for pairs if they are disjoint or not. It is in similar flavors to things like orthogonal vectors, but I don't want to have more definitions.
It's a self-probe.
It's the assumption is in word RAM, I think, actually.
Like you can't do it.
Yeah, so the conjecture is that you can solve disjointness in the word RAM much better than like the trivial thing to do. Okay, and this was like this is like a big like barrier, that thing. So actually it took some time to get there. Like before that, they had some lower bounds, like up to 2 point something that were slightly improved, and the technique they use for these lower bounds kind of very naturally stops at 3. Like they can't get to 3. Yes.
So maybe I missed this, but what again is this query parameter? Like the numbers you're querying?
How much time does it take me to make a query between 2 vertices? Like if you give me 2 vertices, if I could spend as much time as I want, I could just recompute the.
You could ask the question. Make some queries.
Oh, okay.
Yeah, if we think of the graph as being sparse, then I can just remember all of my graph. Let's stay in that regime. So if I had unlimited query time, I could just recompute the distance between them.
I see. So this is the number of queries to the oracle, but are you?
No, this is how much time, again, in some definition of time, it takes to compute a query to the oracle.
It's like you get asked what's the distance between this and this, and then you get to probe your memory.
Because you
That's
pre-process.
the approach you get to make.
Yeah, I have some information. I have, let's say, also the graph because it is sparse. I could just in linear time compute the distance between them, but because I have some extra things that I saved in the pre-processing, I can do something quicker.
Okay.
So I can do something much quicker.
Like alternatively, you could just pre-process by storing the answer to every possible query, and then your
Yes.
program would be order 1. Well, it would be 1, but then your memory gets really bad.
So here you're saying it's order K, but K is like.
I think in the upper it's any K,
Oh, okay.
and in the bottom one.
Yes. So they basically they cared about this trade-off, like how much memory I need to be able to get the K approximation.
Oh, okay.
Okay. So what we are going to show. We are going to show that no m to the 1 plus some constant c over k pre-process time and m to the, and let's say also c over k query time for k approximation for any k. Right, so
Pre-process and memory, I guess.
yeah, so if your pre-process time is limited and the graph will begin with this sparse, then this also bounds the memory, but this is a good point because some people not care about exactly this question, but some people care about the question of, let's say that you can do whatever in the pre-processing and you just want to limit your memory. This is also more interesting if you don't talk about sparse graphs. If you talk about dense graphs, then it makes more sense to spend more time, but have something smaller. So this answers the question in terms of time, more than it is in terms of memory. You're saying that if you are not spending more time than that, and the queries are not linear, basically, then you can't do it for any constant factor. Yes, sir.
K is a constant.
K is a constant. Yeah, but as large as you want. Yes.
And so what's the assumption that this is based on?
Okay, that's a very good question. Then this is if either APSP or free sum. Okay, let's see.
The assumption that they originally had.
Well, it's different because theirs is for memory and this is for time.
Yeah, so we don't, yeah, but we don't.
Oh, yeah.
We don't have the same assumption, right? Like he was talking about the disjointness thing. We don't. Okay. Maybe I should write on a board. I can. No, I actually would want the other board. Okay. Another example from for a problem we are going to solve. And try to sketch what's the intersection between them, is the following thing. Here is a very, very basic question in graph algorithm. How much time is needed to find CK? I give you a graph, I give you some constant K, you want to find a CK in the graph. Most notably, finding a triangle in the graph. This is one of the most problems to reduce to things, to work on, strongly related to matrix multiplication, and so on. You can ask this about cycles of any size. And the landscape about this thing for a lot of time was very, very weird. In what sense was it weird? So we know that we can solve this. So let's think about algorithms in terms of functions of the number of edges. Right, so triangle, for example, we know that we can do with matrix multiplication. We can also do in this type of time, the number of edges to the 1.5. For cycle, in terms of upper bounds, right? These are upper bounds. In terms of upper bounds, we can do m to the 4/3, and so on. But then we might ask ourselves, in the same flavor of everything we have done so far, is there any conditional lower bound for this type of things? And something that people strongly believe, because this is again equivalent to a lot of this equivalent, or stronger than a lot of these previous conjectures, people believe that the triangle should be hard in a few senses. For example, people believe that even in graphs that are somewhat sparse, let's say graphs with n to the 1.5 edges, you still need quadratic time to find a triangle. This would stay true even if matrix multiplication is linear, other things. So people do believe in the hardness of triangle, but we don't want to add more conjectures about the hardness of other cycles. So it would be nice to be able to at least say the following very simple claim, that we can't find any other cycle in linear time in the number of edges, right? Unless we can find a triangle much quicker than we think we should. And this was actually known for many possible values of K, but not for all, most notably not for 4. Right, so open is finding the 4 cycle is in linear time. So what we are able to claim is that the answer is no, that if finding triangles is hard, again, not completely formulating what I mean by that, then no CK is linear at least. So this is actually a bit stronger than this. It shows that there is some like fixed constant such that let's say, such that 4 cycle takes m to the 1 plus this constant, but let's not write ugly numbers. Okay, and I can write another, okay, so there are other corollaries that I don't want to get into too much, but things like the approximation, hardness for approximation of Gare, things like dynamic shortest paths, and other things that I don't want to get into because they are somewhat similar to the things we are going to see. I do want to start by saying a few things about this, because maybe, I mean, my main objective now is going to be to convince you why this like meta theorem we stated in the beginning is going to be helpful for both of these things. Okay, so why is it going to be helpful? How would you, and we will begin with the cycle thing because this is easier to sketch. So how would you go on about this? How would you go on about finding a triangle to finding something that is larger than a triangle? So First of all, and I will just mention it, there is some really simple, really clever technique called color coding. This is by Alon, Euster, and Slick from 94. This is basically saying the following thing. If I have a graph and I want to find some subgraph of size k, let's think of k as a constant, k is free, let's say in our case, I can randomly color the vertices of my graph in k colors, and I would have some constant probability that what I'm trying to find is colored with like one, you can even say like a specific color for each vertex of the subgraph I'm looking for. Why does this help me? Because then I can basically partition my graph to k sets of vertices. And now I know that I need to look for the ith vertex in my subgraph that I'm looking for in the ith set. And also I can remove all edges that are not relevant. So for example, this means that finding a triangle is as hard as finding a triangle in a tripartite graph. Right, so I can assume that my graph is tripartite. I have edges only between the parts, and I need to find a triangle in here, and this would be just as hard as finding a triangle in general. Okay, so this is the first step in any of these reductions. Yes?
So just to make sure I understand, you're saying, suppose we took a graph, we colored it 3 colors uniform, each vertex 3 colors uniformly at random,
Yes,
then we destroy all the edges between
a color and itself.
color itself. Okay, and then with constant probability, we preserve the triangle.
Yes. So do this constant number of times, and this means that this is enough to solve it for the tripartite case. Okay, so if we are in a tripartite case, what can we try doing to translate a triangle to something larger? The first thing to try is to subdivide edges. Right, I can take, for example, all of the edges in this part and to add a vertex in the middle of them. Like the edges in this part and the vertex in the middle of them. I could do it in different parts. I could add several vertices. This doesn't change the number of edges by much. So if the number of edges was m, the number of edges afterwards is like 2m or something. So if I care about complexity in terms of the number of edges, it didn't hurt much. What did it do? So it did translate. So if I added I subdivisions to whatever arbitrary parts, it does translate every triangle to a 3 + I cycle, right? The question is, when is the other side true as well? When is every 3 + I cycle in this new subdivided graph came from a triangle? So here are a few claims without formal proofs. First of all, for k that is odd, it works. I mean, if I want to reduce triangle to something that is an odd cycle, then this would work. Why is that? The claim is that the girth of this graph is k after the subdivisions. Like I can't circle through all of the parts in my graph with less than k. And if I didn't circle through all of them with my cycle, so there is some part that I didn't use, then actually you can notice that the rest of the graph is bipartite. Right? So it has no odd cycles. So if I have an odd cycle of length k, it must be going around everything. So it must have came from a triangle. Another observation is that if k is hard, then so is any multiple of k. Why? Because if you subdivide all of the edges by exactly the same number of subdivisions, then it is also true that everything in this graph would be composed of these subdivided components. Yes.
So by hard, you mean it works, or?
I mean, like you can't do it in linear time. If you could do this in linear time, you could do this in linear time. And everything is a constant. So everything odd works. Everything that is a multiple of something that works. The smallest thing that we didn't cover by this thing is 4. right? And unfortunately, 4 doesn't work. Why doesn't 4 work? So this is the only way to subdivide open to get 4. But now we make the following observation. A 4 cycle is bipartite, which means that I could have just a 4 cycle in these 2 parts. Or I could have just a 4 cycle in these 2 parts. Right, so a 4 cycle in this new subdivided graph doesn't mean that I had a triangle in the original graph. Because actually any bipartite graph can lay in any of these small things, and I didn't subdivide all of them. Right, so 4 is problematic. How can we solve this problem? If the original graph didn't have any 4 cycle, then this is not a problem anymore. Right, so if we manage to get rid of all of the 4 cycles in the original graph, then we are fine. Okay, so this is one example for how we can use that. Now let's try to say something about the distance oracle thing. Yes.
Is the triangle hardness assumption that you can't do it in n to the, oh, it's that you can't do it faster than n squared?
Yeah, so let's say you can do it faster than squared for some sparsity. Okay, so the other thing is actually going to, I don't know who should I cite for this because it appeared in several places, and also we prove it again because we need slightly different parameters. But the following thing is hard from almost whatever assumption you want. So if free sum or APSP, then the following takes this is not a great notation. I mean, you can do it in less than in n to the minus epsilon for any epsilon larger than 0. To get G with max degree, it is at most some constant times put n. And you want for every edge, say whether it is in a triangle. So this is hard. This was known to be hard in several different papers from several different things in several different regimes, even like with these restrictions and so on. This is kind of a really strong version of finding triangles. I want for every edge to say whether or not it is in a
Output is of one.
The output is of the number of edges, so it is of size n to the 1.5 in this case. But yes. Yeah, the root n threshold is a nice threshold because in this point, even if matrix multiplication, like fast matrix multiplication, takes linear time, then kind of the naive algorithms and the matrix multiplication algorithm are kind of colliding in some sense. Okay, so we know this thing, and we are going to want to use this thing to imply hardness for distance oracles. So what does this thing give us, like right off the bat? So we could use this to try to get some hardness for distance oracles in the following way. First of all, let's not go into technical details, but I can still do some color coding tricks and make my graph tripartite as before. Right, I mean, maybe I would need a logarithmic number of graphs, but let's not think about it. Okay, so I can think that my graph is tripartite, and then I could do the following thing. I could take any of the parts, remove them. So it was supposed to be red. Let's remove one of the parts. Then I could apply my distance oracle to the rest of the graph. After I applied my distance oracle to the rest of the graph, I can go over every edge that used to exist in here. Now it's just a pair of vertices that don't have an edge in between them anymore. and ask the distance oracle what is the distance between that node and the other node. Right, the existence of a triangle implies that there is a path of length 2. If there is no triangle, there is no path of length 2. But if there is some path of length k minus 1, then we add a k cycle. So this is how we are going to use again our construction, right? Because if there would be no small cycles except of the triangles, then we would again have this phenomena of the distance oracle would need to distinguish between distance 2 and distance very large constant for our choice. Here I will say something about all of these red nodes. So while for 4 we can actually get rid of all 4 cycles, this is for example what we just used for the 4 cycle hardness. For larger case we don't really get rid of all of them, but we leave a very, very small amount of I cycles for any I between 1 to k up to k of your choice. This is why this needs to be kept in some constant. So you need to choose like when you stop, because then you lose something up to that. But this number of cycles is going to be very small. In what sense very small? It is going to be much, much smaller than, let's say, the number of edges or the number of vertices in the graph. So if I'm starting with this type of problem of answer something for every edge, then what I would be able to do, and this is a bit end wavy, is to say the following thing: do what we said for every edge, and each edge for which the distance oracle returns something that is less than k. This is a potential triangle, but not necessarily a triangle. But the number of these potential triangles would be upper bounded if there are no triangles by the number of short cycles. So if there are only a few short cycles for all of the possible lengths up to k, I would be able to just check this small set of edges. Check like naively, just compare their neighbors. And then this would be enough. So this is why it's enough to still have a small sublinear number of k cycles. Yes, Roy?
This is sanity check that I understand. So the lower bound, the conjecture lower bound still holds if I'm allowed to make a few errors on the small number of edges.
Yes, but in a very small number of edges, like a sublinear number of edges. And also notice that this is a sublinear number of edges out of the edges we asked for. So this is also something to be careful about, right? Because this is not out of all pairs, because otherwise it could be that like my desired pairs, which is it is much less than the possible number of pairs I'm asking for, n to the 1.5 pairs. There could be n squared pairs. So if among the pairs I'm asking for there is a very small error probability, then this is fine. Yes. So
Do you think you could repeat the procedure again for how you're using the distance oracle? I don't think I followed.
yes. So our problem is in a tripartite graph. Let's not talk about why. One at a time, I will remove a part of the tripartite graph. And then I would pre-process what's left into a distance oracle. Now, for every place that used to have an edge between two vertices, now there isn't this edge anymore. What is the distance between them in the remaining graph? So it is either 2 if there was a triangle, or whatever the size of the smallest cycle that contains this edge. Right, so I'm asking the distance oracle for that. And if there are no small cycles or very few small cycles, then it wouldn't be able to answer something that is less than this k, this lower bound on the size of the cycles too many times. Okay, any questions so far about any of that? Okay, so it doesn't look like we have a lot of time. I will try to say something about the proof though, or at least something about the exact statement, but okay, maybe saying something about the proof is more important than saying something about the exact statement. So I will write it down, but I will not go into like all the technicalities too much. or maybe I will even like hide some of the parameters. I'll just give you some flavor of how the statement looks like, and then say something about how we prove it. Okay, so I'm adding a lot of quotes because I'm not going to cite it exactly. Like, it's written more in a more exact manner in the paper. But what we are going to say is that for any choice of k, at least 4, any choice of alpha and epsilon that are small enough. Small enough is going to be a function of k, kind of things in nature. We can take, let's raise it for that. We can take max degree root m graph and in n to the 2 minus epsilon time get a subset E prime of the edges and the list of subgraphs. And we would want the following things to hold. So first of all edges in E prime are in triangles in G, that means. So this is kind of edges that I know the answer for. And the second thing is that every edge that was in a triangle is either in E prime or in a triangle in some GI. So I translate my graph to a few graphs such that the existence of a triangle containing an edge is either preserved in one of the subgraphs, or I know that this edge was in a triangle. So some edges I would just like list outside and say these edges are fine, trust me. And for the other edges, I would just look at these small graphs. Now, two things that I unfortunately don't plan on writing exactly is, first of all, sizes are fine. In terms of S, GI, the number of edges in GI, all of them are small enough for what we are going to need. This means that I didn't do anything too crazy with this partition. And the second thing is that number of CIs in each of this, maybe let's have it CLs, any of these GIs is small. And this will be for every I and every L.
Could that be K? Like whatever K you listed above.
So L is, it can be, okay, so L is at least 4 and at most K. So there are ugly terms in here and ugly terms in here about what are the sizes of the things, what is the upper bound for the number of cycles of every length. These ugly terms are enough to do what we said before. Questions about the statement?
Well, just since you have a bunch of the G's and a lot of S's, how do you run the?
You do everything we said for each of them separately.
Okay, so you have the S is that small.
Yes. And also we said that like every edge, either we already know if it's in a triangle, if it's not anywhere, it's not in a triangle, or that it's in a triangle if and only if it's in a triangle in one of these graphs. So if I have the answers for the same problem in each of these graphs, then I'm fine.
How big are roughly each of the GIs?
Roughly size root L.
It's a number of them. It looks like a basic problem.
Yes, so the number of them is let's say roughly n to the 1.5, like minus something, like you need these things to be, so you want the total number of edges to be polynomially less than n squared. Otherwise, everything we said wouldn't work. So, but it is up to like these savings, it would be something like that. Okay, so now the nice statement replaced with, actually not as ugly as I planned to write, maybe you should be happy. So this is as ugly as this statement is going to get. And in the not a lot of time that we have left, I'm hopefully going to, at least on a very, very, very high level, sketch something about how this is done. Okay. So let's make two observations, and I'm going to phrase it in a.
So can I just ask if like the number of edges is linear and the max degree is like n to the epsilon? Is this meaningful what you get here? Or? So
in not really what we started from in most of the cases is conjectures about something taking quadratic time. So this is kind of saying that you can preserve this quadratic time that it takes. Okay. Let's make two observations. It might take 5 more minutes. Hopefully, this is not too bad. Let's make two observations, and what I'm going to, even in the high level sketch, I'm not really going to give a high level sketch of that. What I'm going to sketch in high level is just for 4 cycles and just for reducing their amounts by much, but not how to get rid of all of them. So this is kind of like the starting point, show that you can really reduce the number of 4 cycles to something that is very small. Okay, so first observation, 4 is larger than 3. Why is that meaningful in any way? Because that means that if I start for my tripartite graph, then I can do something of the following form. I can split each set into many subsets uniformly at random. Let's say that this is roughly root n subsets of size root n. And now every triangle that I add in my original graph is going to be a triangle between a triplet of these small subsets. Right, and if the sizes, I mean, there are epsilons that needs to be in the right, that need to be in the right directions, but the number of triplets of subsets is roughly n to the 1.5. The size of the subsets is roughly root n. Multiplying them is not good enough, right? This is quadratic, but if things are slightly smaller than that, then this is fine. Right, so triangles, if I'm going to split it uniformly and then work on every triplet, then I didn't kill any triangle. I did kill a lot of 4 cycles. Why? Because the 4 cycle survives only if the 2 nodes that were in the same part ended up in the same slice. Right, again, important observation, 4 is more than 3. So one of the slices has 2 vertices, one of the parts is 2 vertices of the 4 cycles. 4 cycle, they need to end up in the same slice. So this means that if I began with C4 4 cycles, then I'm going to reduce their amount by roughly 1 over the number of parts I have in here. Right, and the number of parts I have in here is going to be, so I'm going to reduce the number of 4 cycles by something like minus half plus something. Like it can't be like really root n as we said before, because then it would be quadratic, so it would be plus something. This is problematic. Why is this problematic? I can't really expect doing more than this, but this still leaves me with a super quadratic number of 4 cycles in theory. Why is that? Because the number of 4 cycles can be all the way up to n to the 2.5 in a bounded degree root n graph. Why just think of root n weeks of size root n? Right, number of C4s is n to the 2.5. So even if I manage to reduce the number of C4s by this factor, I don't know what I will do if I had less than quadratic number of 4 cycles, but if I have more than quadratic number, then obviously I have nothing to do in less than quadratic time. I can't even hope to somehow find all of them and do something about them. And this means that the main tool you would really need to be able to do anything would be to say that we can make sure that the graph is polynomially less than n to the 2.54 cycles. All right, so like the first step is going to be C4 needs to go to n to the 2.5 minus some constant. Without that, we have no chance of doing anything. And the way we are going to get something like this is by noticing, well, first of all, let's look at this example. This is the example in which we have a lot of 4 cycles. There is a lot of structure in here. This is very far from just being a random graph. In particular, we have a lot of small subgraphs that are very, very dense. Right, in a random root n degree graph, we expect only n squared 4 cycles. Right, so here we have the maximum number of them, and we have a lot of subgraphs that are very dense. So the way we do this is by having some type of a structure versus randomness result. Right, so in particular, we would want to say something like, if too dense, if we have more than this number of 4 cycles, if too dense, then, and again, a lot of notes, we can quickly find dense subgraph. We'll say something like, if we have too many 4 cycles, then we can somehow quickly find a subgraph that is very dense in some measure. Didn't define the size, didn't define the density, but it would be very dense. And then we are going to realize the following thing. So it's not written anymore, but when we talked about triangles, for example, we saw that we have 2 algorithms to try using. One of them is the naive thing, just, I don't know, compare like the edges to something, and one of them is fast matrix multiplication. And in many places, you can notice that fast matrix multiplications becomes much better when graphs are very dense. The time, for example, in a very dense graph, I have a graph with n vertices and squared edges. The time to compute fast matrix multiplication is n to the 2.37, for example. This is much, much less than n cubed. So when the graph is very dense, this gives me something that is faster than other methods. So in a very high level, what we are going to try doing, or actually what we are doing, is to find these dense subgraphs and then to use something that uses fast matrix multiplication to get rid of these subgraphs. In what sense? In the sense that we can compute the answers to everything, to all of the edges in this subgraph in time that would be good enough, in the sense that because we remove a dense subgraph afterwards, we can't do it too many times.
I interrupt you, but it's 12:30, so we should probably.
Yes. No, this is the last sentence, right? But I will repeat this last sentence. We are going to find dense subgraphs, then somehow find the answer for all of the edges in these subgraphs in a good enough time. And yeah, that's indeed where we
Recurse, you mean, or what?
yeah, we'll do it a lot of times, but because we removed many edges in each of these iterations, because it was a very dense subgraphs, it wouldn't happen a lot of times. because we gain a lot from removing a lot of edges for some price that would be quite low. I mean, it's not completely clear because we need to answer in respect to the entire graph and not only to the subgraph, right? If I remove an edge, I need to know if it is in any triangle in the graph, but still something that uses matrix multiplication in a non-trivial way can solve this faster if this is very dense.
Great. Is there any quick questions? Maybe we'll take them at lunch. Thank you.
Okay.
Great.